So welcome. I'm Jan Čelák. I'm also on the program committee, and welcome to the last session of today. Before we start, one announcement. The registration for the social was extended to till 5 o'clock, so if you want to bring +1 or if you still haven't registered, you have time. And with that, I welcome Petr Špaček of CZNIC, who will be talking about testing server selection of resolvers. Yeah.
Thank you for introduction. So welcome. I have to start with two things. First, this is joint work by me, but I'm mostly speaking and doing design. The dirty work was actually done by my colleague Štěpán Balážik, so most of the credit goes to him. And second thing, this is also a story of a failure in software development. So the fact that I'm working for CZNIC at the moment doesn't mean that I will be working at the end when my boss sees the presentation. So during this presentation, we are talking only about the cache miss situation because we are concerned with server selection, right? So cache hit events are not interesting for this talk. Okay, so server selection, what exactly it is? When we have a cache miss, we have to handle it by going and asking the authoritative servers somewhere on the internet. And typically, there is more than one authoritative server to select from. At the first glance, it might seem like an easy problem, easy task, but it's not, especially because it's complicated by missing glue record, so we have to decide under what conditions we have to resolve the missing IP addresses, or the server might be sending some garbage back, so do we back off or not, and serve stale, and all this complicates the server selection way more than I expected when I started the research. Also, the server selection algorithm can be optimized for different things. It might be number of packets, or we can say bandwidth. It can be non-predictabilities to make a job harder for attackers, or of course it might be RTT if we are in racing game. And implementation detail is that the current open source implementations are, well, pretty messy and complicated when it comes to server selection. Even though it looks like function with 10 lines at the beginning, eventually you will discover all these interdependencies to other components, and usually you just stare at the code and have no clue what it is doing. So when we want to test something which is totally opaque and magic, we have to split the problem to subproblems and solve one after the other. So first step is having a reproducible test environment, obviously, because we want to be sure that we are not seeing just noise. And in second phase, we will be looking at these scenarios for the server selection and the data analysis. So let's start with the reproducible test environment. We have a new tool. It's called DNS maze, because the server or resolver has to go through the maze of the possible paths to the answer. And it's basically mock for the internet. Of course, it's very small internet, but it does all the networking stuff, spins up authoritative servers, clients. If you want to test something with DNSSEC, it can fake the time, so the DNSSEC signatures are not expired if you don't want them, and so on. Design principles here were basically minimalism and speed, because we wanted a tool which can be integrated in continuous integration pipeline for our NOT resolver, so it has to be small and fast. In the end, we just try to reuse as much as possible, including systemd. Even though the opinions differ, it did the job very well. So let me show you example how we can configure our little internet. And the first box, which is called auth, we have declaration for single authoritative server. It has some name. We declare that we use the not DNS authoritative server, some IP address in the mock internet zone file, and most importantly, we have a specification of delay 50 milliseconds. So this instructs the tool to simulate 50 millisecond latency on link. Then, of course, we have to configure the resolver, which is much easier. It just doesn't have delay. It has its config file and IP address, and client is just easy DNS perf with list of queries. Every single query is unique, so it causes a cache miss, and that's it. From these little snippets you see on slide, our tool generates full config files for every single piece of software we are using. Then it generates a bunch of systemd services and runs all the machinery. Eventually, at the end, we get a PCAP with all the packets, and then we can do the analysis on the PCAP. DNS maze is configured using maze of config files. For network simulation, we decided to use Linux namespaces because it allows us to run everything on a single laptop. It's self-contained, it has minimal dependencies, so we are using Linux namespace with dumb interfaces inside for every single IP address we use. And we use something called network emulator, or NetEm, which is a module for a Linux kernel, which allows you to introduce network delays, a packet loss, and all other weird stuff on the link layer. The implementation details are quite nasty, so I will skip over them. We can discuss it on the hallway or over beer. For authoritative servers, the choice was clear. We are using our own DNS authoritative server for the standard zones. So we just give it name of the zone and zone file, that's it. And also we have a support for something called test server, which is basically thing which extracts a queue type and queue name from the query and then can send any byte stream back. So you can simulate weird answers, not only valid DNS answers. And on the last row on the slide, you can see a specification for NetEm, and it says that the link delay is 68 milliseconds and 4 millisecond variance, and 1.48% of packets will get randomly lost. This is how you configure the link parameters. As I said, the client is easy, just list of queries which are unique, so it causes cache miss. The last missing piece is the resolver. The nice thing is that the DNS maze doesn't touch the code of the resolver at all. So you just can use any binary and just run it inside the Linux namespace, network namespace, and it will just work. So we don't touch the resolver under test, we just run it. Okay. The use is basically two phases. First phase, something called process generator is a script which reads the description of the scenario. It will spit out directory full of systemd unit files. And the second script called reload services will just start system or tell systemd to start everything. And then the systemd will take care of the dependencies. So it first starts the network namespace, then the authoritative servers waits for the authoritative servers to start, then start resolver, and so on and so on. In the end, we get a PCAP. Once we have a PCAP, we can look into it and try to find out what's happening. For this second part of the presentation, I strongly recommend people sitting in the back to open the slides on your laptop, because now it will be, circus with a lot of charts. And if you are sitting in the back, you will probably not see very clearly. So, in theory, the problem with scenarios is that in the RFC or on the paper, it seems like, okay, we will do this little test, and that covers what we need, but the internet is more like this. It's just total mess. So what we ended up doing was writing another tool which takes statistical data from RIPE Atlas network, and generates scenario out of the statistical data. So we can say, okay, use this probe on Hawaii, and it will spit out a test scenario for DNS maze, which is simulating the network conditions on Hawaii or any other RIPE Atlas probe. Let's start with the laboratory tests. That's the easy to explain, and then the reality, which will just blow up our minds. The first test case is very easy. We have 10 authoritative servers with latency starting at 10 milliseconds and increasing with step of 10 milliseconds from 10 to 100. So there is no variation in latency, there is no packet loss at all. The easiest thing we can do with the PCAP is just counting packets. So we are looking at the number of queries sent from the client to the resolver and comparing that with number of queries between the resolver and the authoritative servers. You would expect that the number will be kind of close to 100%. And it turns out that the knot is, well, not optimal. So let's dig deeper. We also can count the packets going to different authoritative servers. So this chart is showing the distribution of packets among servers from bind. You can see that bind is very clearly going to the closest or fastest authoritative server. The same for knot. Apparently, the algorithm find out that there is one quick server, but is still sending queries to the slower ones as well. PowerDNS is optimizing heavily for latency. So again, you can see that it's going hard after the fastest server. And Unbound has something which is called RTT band. And all the servers in the RTT band are by default used in a round-robin manner or random, I think. Yeah, it will be random. So Unbound is basically sending queries all over the place. You can see that the bars have a little bit different heights, but that's just rounding errors. So it's like spread among all the servers evenly. Another thing which is in the PCAP and we can analyze is latency of the queries. So in this chart, on the x-axis, we have a number of queries, or well, I should say sequence number of the query. So this is the query first, and this is query 10,000. And on the y-axis, we draw the latency of the queries. Again, you can see that the PowerDNS is going hard after the fastest server. That's the orange line down there. Bind is very close, and it's randomizing its queries way more than PowerDNS, but still keeping very close to the optimum. Unbound, because of its RTT band, is just using all of them, and not never stabilizes and does something crazy. We can zoom into the first 1,000 queries, so we can see the behavior after the resolver start when there is the empty, like network RTT cache, or how we call it. And you can see that PowerDNS takes some time to find out the fastest server, and then it locks on the fastest server and goes on. Bind is doing something similar, but Bind's algorithm takes more time. Unbound is just using all of them, so there is no big jump, and Knot is all over the place. Of course, if we look at the queries in the over whole period of time, it's kind of hard to see with naked eye what is the final latency for the clients. So this is the latency histogram for the resolvers. It was inspired by PowerDNS invention for histograms. So here we have percentile of requests, and here the 10% means, or 10th percentile means that the 90% of queries are in here. So for 90% of queries, we can say the latency for PowerDNS is lower than 20 milliseconds. X's are logarithmic, right? So you can see that all the algorithms kinda optimize or try to optimize, but well, sometimes it doesn't work. In case of Knot, it's just, I don't know. And Unbound is exactly copying the behavior of random algorithm. If we draw another line with like completely random selection of the authoritative server, that's exactly this shape. So that's what Unbound is doing. Okay, that was a bunch of pretty charts. Of course, we have to verify that the result is stable and that we can reproduce it. So what we did is that we ran the same test with PowerDNS 10 times in a row and put all PCAPs and all results in single chart. And you can see that the result is pretty stable. It's like a little bit noisy, but not so much. So we can conclude that the measurement system is doing a good job and it's reproducible. Now we can move to another test case, which is one root server, which is like just for the delegation, so we don't care, and its root server latency is 0. And then we have 5 authoritative servers. 4 of them respond with latency 50 milliseconds, and the last one is dead. That's this missing column. So now what happens? We can look at number of packets. You see that now magically not is fine. And we can look at the distribution of packets for bind. The first column here is the root server, so with latency 0, we don't care because there is just single query for the delegation, and all the rest is happening below on the other servers. And this is the distribution of packets. So bind is trying to find out whether the server, woken up from dead or not. So 1% of queries is going to the dead IP address. For not resolver is kind of same, but the number of packets is higher. For Power DNS, we see that Power DNS somehow decided that one of the servers is much faster, even though all of them have the same latency. But that might be some rounding error inside or something in the Power DNS or something. And finally, unbound. Unbound, again, is spreading the queries evenly because 50 milliseconds is inside the default RTT band. Latency is kind of boring because everyone eventually finds out that, OK, there is nothing interesting, except of the beginning where the resolvers have to find out that there is one dead server and the rest has the same latency. So it is jumping all over the place, and then it stabilizes. Latency histogram is not that interesting, except the fact that some queries take a really long time because they probably go first to the dead server, and then there is some timeout, and then it's retried. OK. Another artificial test case is one server which is super fast, 10 millisecond delay, but it has DNSSEC signatures expired on all the answers. And second server is slow, but it has valid data. So let's see what happens. Number of packets to the authoritative server just explodes. You can see that the bind is, it seems sending query to both servers evenly, and then it finds out, oh, OK, this one is expired, so we will try the other one. Not resolver will send it to the fast one, but well, let's wait for the result. Power DNS sends everything to the fast server, and that's it. And unbound, you see the result yourself. OK, this is the latency over time. The only surprising thing in here is, again, not because the algorithm is just going crazy. This is the zoom in to the first 1,000 queries. You can see that Power DNS figured out in here that there is one fast server, and then it's going after the fast one. And this is the overall latency for all the queries. And you can see here new information which wasn't present in the previous histograms, that Power DNS is surveilling in 100% times because they are not taking into account the bogus answers. And the thing is that the NOT also doesn't consider bogus answers like our business. Well, we are not going to fix problem on the authoritative side. So these two will surveil like all the time, and bind and unbound will give the right answers. That was for the artificial scenarios. Of course, we can invent more, but our time is very limited, so let's have a look at a real board. This is taken from Atlas probe in Prague, and the probe is actually in a data center. For some reason, it doesn't have IPv6, but it has super fast connection to root servers. You can see that 6 root servers have latency about at most 8 milliseconds, plus some variants. So it's super fast, and the rest is slow. Let's see what happens. Bind and NOT, for some magic reason, issue 10% more queries than they would have to. We don't know why, but that's what we measured. And this is the packet distribution. You can see that bind will find out that there are 3, 4 super fast servers and send the queries mostly to them. For not, it's all over the place because the algorithm never stabilizes. Power DNS, again, will find out that there is a bunch of fast servers and hit them all the time. Oh, maybe this slide is messed up. We'll see on the next slide. And unbound, again, is basically sending them all over the place because it's in the RTT band. Latency over time, again, not is doing something funny, and everyone else is doing something reasonable and going to the quick server. Zoom into the first 1,000 queries. Again, there is some period where the resolver is finding out different latencies, then it stabilizes and goes on. Okay, this is latency for the queries. For some reason, the latency is of the connection to the root servers is so small that it's basically dominated by latency in the software and like all the measurement stack, because latency of 1 millisecond is nothing. So it's very hard to conclude anything from this chart. Okay, let's try something more complicated. Now we have much smaller set of fast servers. We have 2, and then other servers are slower and with much higher variance. Okay. Not is doing something crazy, and bind is apparently trying really hard to find out which server is the good one. This is the distribution of packets. It seems that they are going to the right place. And for not, again, it's all over the place, never stabilizes. Power DNS, again, finds out that, OK, these 2 are good. I'm going to use only these, and nobody else is talking to me. And unbound now is using the servers which belong to his RTT band. And you can see that the servers with high latency, like 200-something milliseconds, are not used because that's above the RTT band limit. So these servers will be set aside as a fallback. Latency over time. Again, we can see that the Power DNS and the bind are doing pretty good job when it comes to latency. Unbound is using its RTT band, so it's in the middle of the RTT band approximately, as it should be by design. And not is doing, well, I will not comment on that. Yeah, this is the first phase. Again, the bind has to find out which server is the fast one and slow one, and it takes some queries and some magic happens. And this is histogram. So you get the idea that there is like stable ordering of resolvers. It's usually Power DNS at the bottom, then bind, then unbound, and then not at the very top. The slides have much more pictures in it. I encourage you to have a look. I will just skip over them because there is no time to, describe all the weird corner cases on the planet. Hawaii, that was interesting, Tasmania, and we can go really fancy with RIPE Atlas. They have really good data. And China, this is my favorite. I'll be done in a minute. You can see that okay, that's wrong button. Here, the packet loss is just incredible. Sometimes it's like 20% packet loss. So it depends on how aggressive the retransmit algorithm is. And yeah, not is super aggressive. Yeah, I will skip over this to conclusions so you can catch social. The main limitation is that this is black box approach. We have no idea why the resolver is behaving in that way. What we can say that it's reproducible, and that's it. Have a look in code. Eventually, we will automate the evaluation, so we don't need to look at the pretty pictures, but we will have a script which will tell us that we are really bad and suck at server selection. And finally, once we have the automation, we will rewrite the server selection in not resolver completely, so it starts behaving in like some sane manner. Most importantly, don't draw too much conclusions out of these slides, because if you look at my talk from RIPE 17.9, which was like 2 weeks ago, you will find out that the ordering of resolvers, like not the worst and Power DNS the best, is not matching the results from the measurements which are focusing on throughput. So don't mix up throughput, latency. These are not necessarily connected. So compare this talk with the RIPE one, and you will be surprised. Thank you for your attention.
Thank you, Petr.
Yeah, thanks a lot, Petr. I could listen to that all day. So I have one question, and that was on the DNSSEC stuff. I mean, Power DNS did 100% server fail and not a lot. I mean, I don't see why this is wrong, because I don't think any RFC requires you to retry when you get an answer from a server that is bad, or do you know of any?
I'm not sure myself. It's like matter of opinion, I would say.
Wes Rudiger, ISI, thank you. That was an awesome set of data, and I'm going to go look through it. And not only that, I'm pretty sure I have 2 coworkers that are immediately going to go download your code and try it. So 2 really quick questions. Can you use it to send live requests to a black box that you don't control? In other words, not some...
Yeah, you can, but you have to do some like jumping through hoops with the Linux namespace. But you can connect the real physical interface to the network namespace and then send whatever you want.
And the second one is, did you try rerunning tests, like some of the, especially the DNSSEC failure tests against things multiple times? Like some of the stuff that I've done in the past year has shown that certain resolvers actually behave differently between one run and the next.
Yeah, I think that we didn't try that one multiple times, but we've tried like randomly selected scenarios to make sure that the result is reproducible. But if this one is special, we don't know.
Victor Duchovny, 2 Sigma. The unbound behavior with retrying on serve fail, you showed a result when both servers were in the same RTT band. What happens when one of them is in a completely different RTT band? Did you do that measurement?
I will show you how to write the test case.
Rolf Wilmans, Announce Labs. Thanks for this work. I just want to point out that what you tested are the unbound defaults, and we have configuration options to pick the fastest or the fastest number of servers.
Yeah, I should have mentioned that we are testing default values. We didn't try to optimize anything.
Robert Story, ISI, one of Wes's coworkers who's going to download and play with your code. Do you have the ability to vary what happens with the authoritative servers over time, like servers go down or latency changes?
Yeah, it is there. We didn't show any scenarios, but the support is there, and we did some like basic tests, so it kind of seems to work, but
okay,
yeah,
thanks.
We will appreciate more eyes. Thank you.
Thank you again, Petr. And the last presentation of today's block will be by Ondřej Suri from ISC, and he will introduce us to the DNS Flag Day 2020.
Hi, this is Ondřej, ISC. It's good to be here after this talk for once. I'm not going to talk about the bind, but I'm going to talk about the DNS Flag Day 2020. If you have been at the RIPE meeting, you've probably seen most of the slides, but this is just a friendly reminder that it is still going on, even though the people running the DNS Flag Day has less and less time. So if you want to help, we will be very happy to have you. So the motivation for the 2020 Flag Day is that the IP fragmentation doesn't really work. So there are some like links, if you download the slides, that are clickable. And even if it works, it's not secure enough. There's Fujiwara-san had a really nice presentation about like how to poison the DNS using the IP fragments. So the conclusion is basically that the UDP is really unsuitable for large DNS messages. And it's causing real operational issues around all the globe. And so the goals for the next year, DNS Flag Day, is to eliminate those operational issues and improve the overall security of the DNS. Even though like it's mostly invisible, but it is causing issues. So for eliminating the fragments, basically for large DNS messages, switching to TCP is the way to go. It's happening anyway. And there's no change for small answers. That's fine to send them over UDP. So if your DNS has only small data in it, you'll be fine. Nothing will change for you. There are some existing standards that talk about this, like that the DNS does include the TCP from the very beginning. And the change from the RIPE meeting that we decided that the default DNS buffer size should be 1232. We came up to the number with the consensus. As for the non-compliance to what will happen the next year, so it's the alternative servers that don't listen on TCP if you have large DNS answers. The other side is that where we don't honor the requested DNS buffer size, and the recursive clients that ignore the truncation and don't retry over TCP. So that's most of the non-compliant software. But if you are using the standard DNS, then the DNS software, then you'll be fine anyway. The advantage of the TCP, why? So it hides the IP fragmentation issues at all. It doesn't have the problem. It's much harder to spoof, especially for the low throughput, high value service like CA domain validation, Let's Encrypt, and others. And for DNS bootstrapping, for the CDS key bootstrap. And it's also, as I said, it's already happening with all the DNS over TLS and DNS over HTTPS. That's TCP anyway. So us DNS vendors need to step up and improve the TCP implementations anyway. So this is inevitable anyway, the TCP in the DNS. So for the alternative name server operators and sort of vendors, you should honor the RFC that the DNS also includes TCP. So the other thing is set the maximum DNS buffer size to 1232 to avoid fragmentation, and the defaults in the software next year will reflect this. Also, the alternative server must not send the oversized answers. Again, if you're running bind, unbound, power DNS, not, then you'll be fine, or others. I'm just naming the open source because I'm the open source person. For the recursive name server operations, it's mostly the same. It also includes the firewall. It's often forgotten. So you fire up your bind, and then your security folk will firewall the TCP because UDP is the only way, right? And 512 size. Again, set the client the DNS buffer size on the client, the requested to 1232 to avoid fragmentation, and the resolvers must support the fallback from UDP to TCP on the truncated bit. So this is the test configuration for resolvers. If you want to, you can do that right now. So basically, the change the next year will just involve setting these defaults in the software, and that's it. It will be mostly no code change in the software. So the missing piece is the exact date. We haven't come to set the date, but I think that 1 year from now sort of makes sense because it's still far away from the end of the year. And it's a lot of time for everybody to prepare. We also need more measurements and more communication. So if you want to help us with measurements or communication or whatever, I'll get a bit later. Here are the contact details. We have a website. The discussion is going on the OARC mailing list, the DNS operations. We also have a DNS announce list, or talk to me, or talk to Peter, or talk to LNet Labs and other supporters of the program. we would also like to have you on this page. So if you're a large DNS operator or a DNS software vendor, we would like to, if you would like join the initiative of fixing the DNS on the scale, because we would like to continue making these. I know that the Flag Day is a controversial name, but like these set points where we try to fix the issues in DNS on scale, and that I'm going to stop being the obstacle between you and the social now. But I'll take questions if you want.
Do we have any questions for Ondřej? Please don't forget to state your name and affiliation, please.
Hello, Robert Edmonds, Fastly. So this seems to be about the transport, right? Stopping fragmentation. If it becomes too large, you have to switch over to TCP, et cetera. Have you given any thought to recommendations to users and developers to make smaller DNS messages so they can, keep using the fast UDP transport?
Yeah, that's a good idea. Like recommending the CDSA, for example.
Yeah, for instance, switching to elliptic curve cryptography if you're using DNSSEC. There's a very common pattern where you need to prove your ownership of a domain if you're like signing up for a service, and they'll say, put this giant text record at your apex. Perhaps we should recommend that they use underscore prefix labels dedicated for that.
Yes, maybe, but on the other hand, if you are like authenticated to the service, switching to TCP is a good thing, right? Sort of.
Right. Well,
because
I've seen
it
some
can't be
apexes
spoofed.
with lots and lots of text records, so.
Yeah.
Victor Duchovny, 2 Sigma. A couple of questions. One is there still room to add any more things to the 2020 Flag Day? One of my concerns, is there room for?
So you mean like
So
related to this, or like do more things at the time?
I'm still seeing a fair amount of non-responding based on the RR type. Lots of name servers drop queries when they get an unexpected RR type, like TLSA. What's that? I'd better drop the packet, security issue or something. So this is the Mark Andrews draft that never gets adopted or has never been finished. The non-response draft.
So we like to do one thing at a time. That doesn't mean we can't communicate more stuff, but as for the Flag Days, we would like to do one thing at a time and repeat, rinse and repeat, because so people get used to. So if you look at what happened in the browsers scene, people are used to the TLS change all the time. They need to deploy new HTTP servers and new browsers, so that it keeps working. But with DNS, we don't have this like mindset, because DNS was always like, I set it up in 90s and it still works. And we want to break this pattern of like, we don't have to touch DNS. No, you need to take care of your DNS.
Right. So the other thing I still see a lot of is on a small scale, but it's the dominant thing, is broken denial of existence. It's kind of neglected and under-tested.
So I generally agree with you, because the DNS is complex enough even without the workarounds. So over time, if we can get to the point where the DNS software doesn't have to have all these like little knobs and all these little workarounds for all the breakage, that would be great. Okay. So sure, we will keep coming, and if it's causing troubles, then I think it's fine to say it's not the DNS vendor's problem. It's your problem. Your DNS is broken, not ours. Okay. So that's the overall notion.
Okay. And lastly, I want to answer a little bit of the last question that was asked, and that is something VeriSign's doing is for UDP fragmentation is keeping their zone signing keys for RSA at 1280 bits or lower, which leaves enough room for NSEC3 answers not to overflow the recommended MTU. So if you're still doing RSA, consider 1280 bit ZSKs, maybe slightly weak RSA keys, but not too bad, really.
Okay.
And then, of course, ECDSA is better. The other thing is if a zone doesn't need NSEC3, NSEC answers are smaller. They usually have one less signature in them. So that's also recommended, is NSEC rather than NSEC3. And then, of course, truncation is always, and TCP is always a good thing. I've seen some zones when they increase query rates and they decide, maybe it's an attack, instead of cutting me off, they start returning no answers at all and TC equals 1. And then I switch over to TCP and then they provide a more generous rate limit. So that's actually a good thing to do in terms of preventing abuse with forged UDP. You can allow a higher rate limit for TCP queries.
Yes.
And that works pretty well as well. Recommend that. That seems to be a good idea.
Yeah, the idea of recommending like keeping the answer small is like both of your ideas are really good. Thank you for that. Manu.
Hey, Manu Brotel, Facebook. In the previous flag day, the DNS compliance test tool has been super handy to be able to validate the authoritative server. It would be nice also if these tests could be added in some ways.
Yeah, we are working on that, but we are like spread it thin. So again, if you have any resources that you can contribute to that.
Okay, I could try to, same resources too.
Thank you.
But I guess we will need in this case to say, hey, please put this long TXT record somewhere in your zone, because otherwise, it would be pretty hard to simulate the large payload.
Hello. Kazunori Fujiwara, JPRS. First, reference may be changed because there is BCP RFC 8085 UDP usage guidelines. Section 3.2 of RFC 8085 specifies that an application shouldn't send UDP datagrams that result in IP packet that exceeds the MTU along the pass MTU. And second comment, I think we can use IP don't flag option, IP don't flag socket option.
And yes, but that's basically implementation detail for the software vendors. But and again, I think that things that you talk about and Victor talked about comes from the fact that people think that writing DNS server is easy. It's not. So if you ever think of writing DNS server, please come to DNS-OARC, talk to us, and collaborate, because we've been there and we've been like burned by DNS many times, and we can show you the scars, and maybe you can avoid being hurt by DNS. Although we like love DNS much dearly here, we've been hurt by DNS many times, and if you think that it's a good idea to write your own DNS implementation because you need some feature that's not available anywhere else, then at least be part of this community so we can help you and we can help all the whole DNS ecosystem. And thank you for the comments.
And next comment is, proposed changes may be deployed incrementally, not a flag day.
Oh, sure. Well, the flag day is a misleading name, but it's a bit of marketing because it draws the people's attention that something will happen and word will end. But basically, for us, it means that we will change the defaults, but not retrospectively. There will be no code in the DNS servers, then when the date hits, everything starts behaving differently. But if you deploy a new version that's after the date, then the default will be different. That's the thing. It's just like the name is to draw attention, and I apologize for that, and I apologize to Paul Wouters, who is. But it helped. It really helped last year with the DNS Flag Day 2019. that like we did something as a community, and we did change the DNS. So that was a great thing.
Okay, thank you, Andrzej, for your presentation. So that was the last one, but I have a couple of announcements here. We still haven't received many Lightning Talks proposals, so if you have some topic in mind, please submit them via Indico. You will find a link on the website. On the left side, there's a call for Lightning Talks, and please submit them by tomorrow, 9 a.m. There's also PGP signing session tomorrow, so if you want to participate in that, you will have to send your ASCII export of the public key to an email address. You will find it, you will find the address and all the instructions. Also on the timetable in the detail of the PGP signing session. Also, please don't forget to fill in the surveys. The link you will find again on Indico. We take these surveys very seriously because it helps the program committee to pick the right content that you will enjoy. So please don't forget to do that. We mustn't forget about our sponsors. So we would like to thank the Comcast for sponsoring this particular workshop, and also VeriSign, who is our annual workshop patron. So has a great contribution to this as well. Couple of information for the social. You might follow Anand's example and dress up. It will be really chill, so take some warm clothes, and you should have received all the information how to get to the dock by email from Indico. There's a map, and it takes approximately 15 minutes to get there from this venue. And please be there sharp on time because we have to leave to see the bats. And the last information, sorry, there's a lot of stuff. Tomorrow we will start at 9 a.m. So thank you for coming today, and see you tomorrow.